Hey folks, thought we'd work through the final exam practice, give you some solutions for most of them here. And number one, you're asked to determine exactly the 6 trig function values for theta equals 4 pi over 3. And hopefully by now the unit circle is pretty firmly implanted in your brain and you can quickly figure this out. As always, I'll try to sketch a quick unit circle. And yeah, it's not too bad. So 4 pi over 3, that's an angle that's terminating down here in quadrant 3. And the coordinates of that point, you should know the coordinates of that point are negative 1/2, negative square root 3 over 2, which then tells you that the sine of 4 pi over 3, it's the y coordinate, so that's negative square root 3 over 2. And the cosine of 4 pi over 3, it's the x coordinate, so that's negative 1/2. And then the tangent of 4 pi over 3, well, you know that's sine over cosine, and sine over cosine here will simplify to just the positive square root 3. And then the other 3 are free using our reciprocal identities. So we have cosecant of 4 pi over 3 is negative 2 over square root 3. Secant of 4 pi over 3, that's negative 2. And then finally the cotangent of 4 pi over 3 is 1 over the square root 3. And again, for those of you that are calculus bound, I cannot begin to impress upon you the importance of just this basic structure, the unit circle, and knowing the unit circle. So hopefully that's what you have for number one. All right, hey, here in number 2, you were asked to convert a point to polar coordinates, and you were told that r has to be greater than or equal to 0, and the angle theta has to be between 0 and 2 pi. So you were asked to convert the point to negative 1, convert that to polar coordinates. And let me write down again that the directed distance r is greater than or equal to 0, and you were told that the directed angle is between 0 and 2 pi. You know, anytime I'm asked to convert a point, a rectangular point to polar, or vice versa, the first thing I'm going to do is just plot this point. I know this point is living about right there. It's living down in quadrant 4. Okay, so now I need to take this rectangular point and convert it to polar coordinates. Just remember, polar coordinates are of the form r theta. R is the directed distance from the pole, and theta is the directed angle. So the conversions that I need to use here are the following. X squared plus y squared equals r squared. And then tangent of theta is y over x. So let's get the value for r, our directed distance first. We know x is 2 and y is negative 1, so I toss those in here for x and y. So I have a 2 squared plus a negative 1 squared is equal to r squared. 2 squared is 4, negative 1 squared is 1, so 4 plus 1 is 5. So I have 5 is equal to r squared. And when I take the square root of both sides, I get plus or minus the square root 5 is equal to r. But since I gave you those directions to use the positive directed distance, for this problem, we will use r, is the square root of 5. So now I need to figure out what my directed angle is. Well, tangent theta is y over x, so that'll be negative 1 over 2. So tangent theta is -1/2. The exact value for theta, the exact value of theta is inverse tangent of -1/2. Okay, now why don't we get a decimal approximation for this? Let's use our calculator. Make sure your calculator is in radian mode. So let's fire up our calculator. And on my calculator, when I do inverse tangent of -1/2, I get theta is pretty close to -0.4636. I'll just round off to 4 decimal places. I can't use this value of theta. My directions. Theta has to be between 0 and 2 pi. Clearly a negative number is not between 0 and 2 pi. None of this should really be a surprise though. Remember inverse trig functions. Remember inverse tangent will find an angle off the right half of the unit circle. This angle is a negative, it's a negative angle measure. So that means all the calculator has done for us, it's found an angle on the right half of the unit circle, and the angle that it has found for us is that angle right there. But we can't use it. Well, here's the quick fix to get the angle we can use. We just need to simply get the angle that is coterminal with that -0.4636. This purple colored angle that I sketched here is coterminal with the -0.4636. So to get that coterminal angle, we just simply take what the calculator told us and add 2 pi to it. That will give us the coterminal angle. And if you do that, you'll get a theta value of pretty close to 5.82. And 5.82 is between 0 and 2 pi. So we have our r, we have our theta. So our answer, to answer the question, polar coordinates, put it in the correct form, our answer would be square root 5.82. So this rectangular point, we'll have this as polar coordinates, square root 5.82. Hope you got that. That's it for number 2. All right, hey, here in number 3, you were asked to convert a rectangular equation to a polar equation. And the rectangular equation you were asked to convert to a polar equation was 3x minus y equals -2. Okay, some conversions that you need to remember in the polar to rectangular world and vice versa. You need to remember that x equals r cosine theta and y equals r sine theta. So if you remember x is r cosine theta and y is r sine theta, you just simply substitute r cosine theta in for the x, substitute r sine theta in for the y, and you would get 3r cosine theta minus r sine theta equals -2. And now what I would do, and I think it's good form, it's good practice, over here on the left side I'd factor out the r, and I have a 3 cosine theta minus a sine theta equals -2. And then divide both sides of this equation by 3 cosine theta minus sine theta to get r equals -2 over 3 cosine theta minus sine theta. You know, if I wanted to graph a polar equation and I wanted to use my graphing calculator, I would need to have it into this r equals form. So that's why I come down to this, and I think that's a good answer. So hopefully you got that for number 3. All right, hey, here in number 4, you were asked to convert a polar equation, r equals 2 cosine theta. You're asked to convert that to a rectangular equation. So r equals 2 cosine theta That's your polar equation. And we want to convert it back to a rectangular. We want to convert it to an equation where we see x's and y's. Well, remember x is r cosine theta. Y equals r sine theta. I might as well write them all down. X squared plus y squared is equal to r squared. And tangent theta is y over x. These are all the conversion formulas you need to know to go from rectangular to polar or from polar to rectangular. Since I want to take this polar and put it into a rectangular form, I kind of look at the equation and I'm thinking, if only I had an r right here, if this said 2r cosine theta, I know r cosine theta is x. So if I only had an r there, I would be able to replace the r cosine theta with x. Well, let's get an r there. Let's just simply multiply both sides of the equation by r. So I have r squared equals a 2r cosine theta. R cosine theta, that's x. And heck, look here, r squared, that's x squared plus y squared. So I substitute x squared plus y squared in here for the r squared. And I substitute x for the r cosine theta. And I have a rectangular equation. You could, if you wanted to, by the way, I am fine with that. But you could, pulling the equation over here, you could subtract the 2x from both sides of this equation and say, hey, that's my rectangular equation. Nothing wrong with that as a rectangular equation either. It's a good rectangular equation. You could do one more thing. You could complete the square on this x squared minus 2x part. To do that would require you to add 1 to both sides of the equation. So that's just completing the square. And now you have a perfect square here. X minus 1 quantity squared plus y squared equals 1. And some would say, let's go with that as our rectangular equation for this polar equation. The only benefit of this would be that this rectangular equation, if you think back to college algebra, this is the general form of a circle. This says this equation represents a circle that has a center at 1, 0 with a radius of 1. So that would be the one benefit of doing all this extra algebra to get to here. But to recap, here's your polar equation. This is a satisfactory rectangular equation for this polar equation. This would also be fine, and this would be fine. So I personally would accept any of those three. Hope that's what you got for number 4. All right, folks, let's look at number 6. If you're wondering, whoa, wait a minute, Billy, you skipped number 5. Yes, I did skip number 5. Number 5 is sketching the graph of r equals 3 sine theta. And I would use my graphing calculator to quickly get the graph of r equals 3 sine theta. I have a lot of things here in my house, but I don't have an overhead unit to shine it up here. But I would expect you, at this point in time, you know how to use your calculator to graph r equals 3 sine theta. Quickly make sure that you know your calculator's in radian mode and that it's in polar mode. And I would make my theta min 0 and my theta max 2 pi when I sketch that graph. So that's all I'm going to say about number 5. In number 6, you're asked to take a complex number and write the complex number in rectangular form. So there were 2 forms on complex numbers here. The form that you were given, z equals 10 cosine 5 pi over 3 plus I sine 5 pi over 3. This form is called the polar form of a complex number. Some people will call it the trigonometric form of a complex number, but your textbook calls it the polar form. I'll call it the polar form. I actually prefer to call it the polar form because it kind of takes us back to the idea of polar coordinates. But in any event, you want to take this and you want to convert it to rectangular form. This is a pretty straightforward problem to do. In fact, it's almost like a Nike problem. You know, you just do it. You just write down what the cosine of 5 pi over 3 is. And that goes back to your unit circle. Knowing where 5 pi over 3 terminates, the x-coordinate of that point on the unit circle. So you should have the cosine of 5 pi over 3 is 1/2 plus I sine of 5 pi over 3. Well, you should know on the unit circle where 5 pi over 3 intersects the unit circle, the y-coordinate of that point is negative square root 3 over 2. So the sine of 5 pi over 3 is negative square root 3 over 2. And then if you just simply distribute the 10 times 1/2 is 5. 10 times this negative square root 3 over 2 gives you a minus 5 square root 3 I. And that is the rectangular form of the complex number. Pretty straightforward. I hope you find that to be a very easy problem to do. But that's it for number 6. All right, hey, here in number 7, it says, consider the complex number z equals -1 minus 3, or minus square root 3 I. And you're asked to do two things: determine the absolute value, and then write the complex number in polar form. So we want to put it in a form like what we saw there in number 6. So let's see, number 7, z equals -1 minus square root 3 I. You know, the first thing I'm going to do is plot this point. You know, keep in mind when we make a good old x, what looks like an xy coordinate system. This is the real axis, and this up here is the imaginary axis. So the real part of this complex number is -1, and there's the imaginary part. So if I plot that point, I don't know, it's about right here somewhere. That's my complex number here. So it's about right there. And remember the absolute value. Absolute value is really this distance right here. And you know, we can do that real quickly. That's something you were asked to find. The absolute value. So remember, for absolute value, it's the square root of a squared plus b squared. So the absolute value is the square root. A is -1, so we have to square that, plus b is negative square root 3. So negative square root 3 squared. And if you take -1 squared, that's 1. Negative square root 3 squared is 3. So you have the square root of 1 plus 3, which is 4. So we have the absolute value is 2. Now we're going to find the argument here, the theta. Well, here's how I do it. Tangent theta is b over a. So tangent theta is b over a. So I have tangent theta is negative square root 3 over -1. Tangent theta is square root 3. Now if you're really good with the unit circle, and you're really good with these angles on the unit circle and the x's and y coordinates, it doesn't take too much effort to realize that theta, for this problem, theta is pi over 3. I can't use pi over 3. I can't use that in writing this in the polar form, because think about where pi over 3 would terminate. pi over 3 is an angle that would terminate about right there. So there's pi over 3. My point isn't up here in quadrant 1. My point's down here in quadrant 3. So how am I going to get an angle that brings me to here? Well, I think the answer is in the figure. If this is pi over 3, this angle down here, we have a straight angle. A straight angle means all I need to do is just add pi to pi over 3. So I take this and I add pi, and that gives me the angle I need to use for the polar form of this complex number. So now remember, the polar form of a complex number is r, and here we found r to be 2. So it's r cosine theta, theta is 4 pi over 3, plus I sine theta. And that is the polar form of that complex number. So that's it for number 7. Hope you got that. I hope everything's going well so far on this practice final. All right, hey folks, here on number 8, I gave you a Z1 and a Z2, so I gave you two complex numbers in polar form. And I asked you to find Z1 times Z2 and Z1 divided by Z2, and to write your answer in polar form and keep the argument in radians. So let's see, Z1 times Z2. You need to remember that at Z1 times Z2, you will do R1 times R2, and then you have a cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. So for this problem, R1 times R2. There's R1, there's R2. So R1 times R2, that would be 2 times 3, so that's 6. Cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. We need to clean this up just a little bit. We need to get a common denominator here to add those two fractions together. So I'll just tell you, I'll talk you through it. Common denominator for these fractions would be 12. So you'd have to rewrite this as 9 pi over 12. And this would be 22 pi over 12. So 9 pi over 12 plus 22 pi over 12 will give you cosine of 31 pi over 12. Now, technically speaking, our argument here should be an angle between 0 and 2 pi. 31 pi over 12 is a little larger than 2 pi. So what I really should do is subtract off a 2 pi from the argument, 31 pi over 12. And remember, when I subtract off a 2 pi, all I'm doing is finding an angle that would be coterminal with 31 pi over 12. But 2 pi is 24 pi over 12, so I should subtract that off and get my answer of 6 cosine 7 pi over 12 plus I sine 7 pi over 12. And well, that's what the answer. Hopefully that's what you have for Z1 times Z2. So to recap, to multiply them together, multiply the r's together, gives you a 6, and then you add these angles. You add those arguments together, 3 pi over 6 plus, or 3 pi over 4 plus 11 pi over 6. Common denominator gives you the 31 pi over 12. larger than 2 pi, so you have to subtract off of 2 pi to get an angle that's between 0 and 2 pi. So hopefully for the multiplication part, you got 6 quantity cosine 7 pi over 12 plus I sine 7 pi over 12. To do the division, that's Z1 times Z2. To do the division, well, it's R1 over R2 cosine theta 1 minus theta 2 plus I sine theta 1 minus theta 2. So instead of multiplying, we divide. Instead of adding the angle arguments, we subtract them. And if you do this, you should get a 2/3 cosine. And I'm kind of running out of room here, so I'm going to talk and skip a step. Instead of 3 pi over 4 plus, it's going to be 3 pi over 4 minus 11 pi over 6. Common denominator. So if you do 3 pi over 4 minus 11 pi over 6, you're going to get negative 13 pi over 12. If I subtract, I get a negative 13 pi over 12. And we have a little bit of a problem here. Again, technically speaking, your angle argument here should be an angle between 0 and 2 pi. Negative is clearly not between 0 and 2 pi. So what I need to do is just add 2 pi to this. That way I will have a coterminal angle. And I would get the answer of 2/3 cosine. If I add 2 pi to this, I should get 11 pi over 12 plus I times sine 11 pi over 12. So that's what you should have for Z1 divided by Z2. I always thought these problems were very straightforward to multiply and divide two complex numbers that were written in polar form. I thought it was very friendly. It's very friendly to multiply numbers and then to just add, or to divide numbers and subtract. So hopefully you got this for Z1 times Z2, and hopefully you got this for Z1 divided by Z2. And that's it for number 8. All right, here in number 9, and kind of like the rest of the problems here, we're into the vector part of the final exam. So in number 9, you're asked to determine the component form of a vector that has an initial point at -3, 11, and a terminal point at 9, -5. So if the initial point is -3, 11, and the terminal point is 9, -5, the vector in component form is 9 minus -3, comma, -5 minus 11. Always kind of remembered it as the terminal minus the initial. So the final answer here is just simply 12, -16, with these funny kind of pointy thingies. So that's your answer for number 9, the vector in component form. And hopefully you got that. All right, hey, here in number 10, you're asked to find a unit vector that's in the same direction of the vector given to you in component form as being 5, -12. So if your vector in component form is 5, -12, and you want to get a unit vector that's in the same direction, there are two things you have to do. The first thing, so I'll call that first, you need to get the magnitude of vector v. And one of the benefits of having a vector in component form, remember a vector in component form, its initial point is the origin, and that gives you the coordinates of the terminal point. And one of the benefits is in getting the magnitude, it's just simply the square root of those individual components squared and then added together. The distance formula, in other words, condenses down very nicely. So the magnitude of V, well, that's the square root of 25 plus a 144, and 25 plus 144 is the square root of 169. The square root of 169 is 13. So the magnitude of this vector is 13. Then the next thing you do is remember that the unit vector has the form 1 over the magnitude of V times vector V. So it's this scalar times vector V. So for this problem, you'd have 1 over the magnitude of 13 times 5 negative 12, which gives you 5/13 negative 12/13. That is the unit vector that's in the same direction as the vector 5 negative 12. And just remember what a unit vector is. Unit vector is a vector that would have a magnitude of 1. So that's it for number 10. Hopefully you got that for the unit vector. All right, hey folks, here number 11, you're asked to find the dot product of two vectors. And the two vectors that you were given, vector u was a negative 2, 5, and vector v is negative 1, negative 2. So the dot product, very, very friendly. U dot v. Here it's negative 2 times a negative 1 plus 5 times negative 2. So dot product is this times this plus this times this. So negative 2 times negative 1 is 2. 5 times negative 2 is negative 10. So we get the dot product to be negative 8. And that's it for the dot product. So hopefully that's what you got for number 11. And that's it. Hey folks, here in number 12, I ask you to determine an angle between two vectors. Well, the vectors that I gave you were, let's see, vector u is 2I minus j, and vector v is 6I plus a 4j. So to find the angle between these two vectors, well, here's our handy dandy little formula. Cosine theta is u dot v divided by the magnitude of u times the magnitude of v. So it looks like we have to find some stuff in order to use this formula. We're going to have to find the dot product, and we're going to have to find the magnitude of each vector. So let's come over here, and let's do the dot product. U dot v is, well, it's going to be a 2 times 6 plus negative 1 times 4. So we get the dot product to be 12 plus negative 4, which is 8. So the dot product is 8. The magnitude of u, that's the square root of 2 squared plus a negative 1 squared. So 2 squared plus a negative 1 squared. And 2 squared is 4, negative 1 squared is 1, so 4 and 1 is 5. So the magnitude of vector u is square root 5. The magnitude of vector v is the square root of 6 squared plus a 4 squared. 6 squared is 36, 4 squared is 16, 36 plus 16 is 52. So the magnitude of vector v is the square root of 52. So we have all the parts and pieces for this formula. So we just substitute in, and we have cosine of theta is u dot v, which we found that to be 8, over the magnitude of u, which is the square root of 5, times the magnitude of v, which is the square root of 52. So this is what the cosine of theta is, which means to get theta, we will use inverse cosine. So it's inverse cosine of 8 over the square root of 5 times the square root of 52. And when I use my calculator, and oh, by the way, when we find an angle between vectors, let's find them in degrees. Let's get a degree measure. So I put my calculator in degree mode. I do inverse cosine of this mess, and I get the angle between the two vectors to be pretty close to 60.3 degrees. So hopefully for these two vectors, that's what you ended up for an answer as the angle between the two vectors, something about pretty close to 60.3 degrees. And that's it for number 12. All right, hey, here in the last one, number 13, I asked you whether or not two vectors are orthogonal, parallel, or neither. And the two vectors I gave you were u equals 3i plus a 15j, and vector v was a negative I plus a 5j. Okay, in the vector world, the word orthogonal means they would meet at a right angle, a 90-degree angle. So two vectors are orthogonal. Let me write this down. Two vectors are orthogonal. It's the symbol I use for orthogonal. If their dot product is 0. And that literally comes from, well, if you look back to the last problem, the little formula for angle between two vectors. So if the dot product of two vectors is 0, you know the two vectors are, are orthogonal. Well, if we do the dot product here for u and v, u dot v is 3 times a negative 1 plus a 15 times 5, we get the dot product to be 72. That's not 0. So these two vectors are definitely not orthogonal. Now for two vectors to be parallel, in order to be parallel, the two vectors have to be scalar multiples of each other. Or in other words, this vector times a scalar will give you this vector, or vice versa. So in order to be parallel, they have to be scalar multiples. So here's how I look at it. Here's how I attack it. I look at vector v and I look at vector u, and I just look at the numbers living in front of the component, the I component. And I was like, well, what would I have to multiply vector v by? What would I have to multiply this by right here to get a positive 3i? And it's like, well, that's a negative 1. I'd have to multiply it by negative 3 to get a positive 3i. So I just say, well, what is negative 3 times vector v? So I have my vector v, I multiply it by negative 3, and that would give me a positive 3i minus 15j. 3i minus 15j, that is not vector u. Close, but this is plus, not minus. So these two vectors are not scalar multiples of each other. That means they are not parallel. Well, if they're not orthogonal and they're not parallel, then the only thing that we could conclude, the only answer that makes sense here is neither. They are neither orthogonal nor parallel. So to recap, if your dot product's 0, you have orthogonal vectors. If they're scalar multiples of each other, they're parallel. If this had been a minus for vector u, if it had been a minus, then the two vectors would have been parallel. But it's not, so the answer here was neither. And that's it for number 13. That's it for the practice final exam. I hope this is making sense. I hope you're doing really well. Hope you got all the correct answers. Hope you're feeling confident for your final exam. Be aware of your final exam. The due date is Tuesday, December 10th. That's the last day to take the final. And I hope you all do as well on the final exam as you have on the other tests. You've done a great job on the tests. So that's it. Thanks for watching, and I hope you found these video solutions I've put together for you this semester to have been beneficial. Have a good one.